I'm very happy to introduce Alan. Alan's been here this week, and he's just a delightful person to work with, so I know many of you have gotten a chance to chat with him. But yeah, he started his work really looking at like variable resolution CESM runs, and it has transitioned into some like convergent focused work with hyperfacets and kind of leveraging stakeholder inputs and stakeholder feedback to get really relevant hydroclimate research and how we're expected to see hydroclimates respond to future climate change. So Alan's a great person to have here at RAL. Please keep in touch with him, and without further ado, please come up, and yeah, we're looking forward to what you have to say.
Thanks, Jacob.
Yeah.
So it's been really great to be at RAL the last week. I've been honored to have come here because of Jacob, teaching him how to use this thing called BetaCast, which allows us to use Earth system modeling tools as weather forecasting tools. So we'll talk a little bit later in this presentation about how we use that tool to recreate a famous rain on snow flood event in California. And it's also been really great to get to know Jacob's dog, Lewis, and he's really treated me really kindly. So I just appreciate all the hospitality I've gotten at NCAR and feel really fortunate to be here. Again, in this talk today, it's going to be focused on snow. And so I thought it'd be important, probably it might be review for folks here, but just wanted to explain why snow is central to Western U.S. water management. Maybe show some of the observed trends over the last few decades before I show the virtual snow changes that I'm going to show, because I primarily use models to investigate snow changes. And then I'll highlight how extreme events can really reshape the snow season. And so I've really been focused over the last 3 or 4 years on these things called rain on snow events and snow or heat wave events. And so I'm using different methodologies to get at these two event types, and I'll talk a little bit about that in the talk today. So as a little primer, in the Western United States, one of the dilemmas that we have is that we get a lot of our precipitation in a short window of time. So this plot here is showing the number of days per year it takes on average to reach our 50% water year total. Now, as you can see in places like California, Nevada, even parts of the Rockies, we can get about 50% of our precipitation in about 5 days, all the way up to about 15 days. So we really get a short amount of time to build and receive precipitation and build snowpack, and so we're really susceptible to interannual variability associated with atmospheric river activity. Now, that precipitation is also already occurring. This is a little bit of an older plot. I wish there was a newer one to use, and I haven't found it quite yet, but it's showing on days of precipitation, are you at or near freezing, meaning are you around roughly 0 to -2 degrees C, and what it's showing is that on an average day during precipitation, up to 40% of that precipitation is already occurring right around freezing, especially in places like coastal mountains like the Cascades and the Sierra Nevada. And the reason for that, as I was alluding to just a second ago, is that we get these things called atmospheric rivers. And so these atmospheric rivers really deliver precipitation primarily as rain, but also as snowfall in the winter months. And they come in bursts of rainfall. So extreme ARs can carry more water than about 7 to 15 Mississippi rivers, which is pretty amazing. They're often seen and tracked using something called integrated vapor transport. And so on the lower left-hand corner there of the screen, it's showing an animation of satellite imagery data of a strong AR event in January 2017. And it's kind of showing the integrated vapor transport plume of that atmospheric river. On the right here is kind of also showing that ARs originate throughout the North Pacific, with more intense atmospheric rivers originating further west in the North Pacific. And so part of the reason why that precipitation during these events is right around freezing is because there's not that much time to cool as they make landfall. And so in a warming world, more of that precipitation might come as rain rather than snow, and that creates a dilemma that I'll get into in just a second. So I'm going to be using this term throughout the talk, and maybe this is review for a lot of folks. We're often talking about snowpacks and trying to standardize them around the Western United States because some are more fluffy than others. They have more air pockets. They have different crystal structures. So we use this metric called snow water equivalent to sort of compare apples to apples between snowpacks around the West. And so for a given snow depth, for example, on the left there, you would get 10 inches of snow depth, but you would get 5 inches of SWE, whereas maybe a fluffier snowpack, maybe that happens in the Rockies, you get 20 inches of snow depth, but only 1 millimeter of SWE or 1 inch of SWE. And so we use SWE, and we'll be using this throughout the talk. Now comparing snowpack storage, I really like this diagram by Dettinger and Anderson. Shows sort of the April 1st snowpack. So in the Western United States, traditionally, water managers have assumed that snowpack peaks around April 1st, and that's when we should start assessing how much water volume we might have stored up in our snowpacks and how much we might expect as reservoir inflow in the spring and summer. And so what this diagram is showing is from 1970 to 2023 or 2024, how much does April 1st snowpack, so that white bar on top of each of the years there is showing the April 1st snow water equivalent in million acre feet across Sierra Nevada compared to 12 major reservoirs in California, so Shasta, Oroville, some of the biggest ones in the northern part of the state, especially in California, and also the 148 other reservoirs. And so essentially snowpack adds an additional 70% additional natural storage through snow water equivalent each year, about 17 million acre feet on average, although there's a lot of interannual variability in that. And so this is in California. I thought I'd also show these really cool diagrams that Dettinger and others put on a web page, and you can monitor the snowpacks as they're progressing through the year. And this is for the Upper Colorado River, Upper Colorado, and it's showing water stored in snowpack, Lake Powell, one of the largest reservoirs, if not the largest in the West, and the 20 upstream reservoirs in the Upper Colorado River Basin. And as you can see, it's showing the seasonality of it rather than that year-to-year variability I was showing before. And so what it's showing is that snowpack on average, which is that white sort of curve, really is even more of a provider of water than most of the reservoirs in the Colorado. So Colorado is even more sensitive maybe to snowpack interannual variability. What is shown overlaid on this as well are the lines and traces of if you do Powell plus upstream reservoirs plus snowpack is the light green line. And what you can kind of see is that there was a dramatic decline in snowpack right around in March. And I'll get into some work that we've been doing on snow water heat waves, and we kind of show that these events often lead to rapid ablation of the snowpack. And so that's what happened this past year in a very, unfortunately, timely way. So now I just wanted to highlight that, April 1st SWE storage and what it looks like across the West and what are the trends in that since the 1950s. So each of these circles here is showing an increasing or decreasing trend in SWE at all the monitoring sites. Red means decreasing trend, blue means increasing, and the size of the circle represents the trend size, ranging from negative 80% to positive 80%. And so across 81% of the stations, we've had about an 18% decline in snow water equivalent over the last few decades. Interestingly, the southern Sierra Nevada and California looks different than the rest of the West. And that is because of 2023. It kind of shifted the trends in a lot of these stations. And so California especially is really can swing back and forth in terms of trends and changes in SWE just by a single year alone. And so it's a little bit unique relative to the West, and we'll talk about Northern Sierra versus Southern Sierra impacts during a rain-on-snow event later in the talk. Another thing that's happening is that for every degree Fahrenheit of warming, that assumption of April 1st being the peak timing of SWE is being eroded because warming is moving the peak timing earlier and earlier in the water year. So for every degree Fahrenheit of warming, on average across the West, we've seen a negative 4 days movement in that peak SWE timing. And that's really important because in a diagram here in one of the review papers I was a part of in 2021, we're highlighting that a fundamental assumption of the Western U.S. water management and energy supply portfolio for hydropower assumes that we're going to have a reliable snowpack. And so the snowpack is represented as sort of a blue underlay on this diagram on the left. And reservoirs and conveyance infrastructure and stuff, and also natural streams are shown as an overlay of circles. Red would be conveyance, and blue would be natural stream flow. And what you can see is we put a lot of our infrastructure right downstream of where the mountains are, and especially in places that are snowmelt fed. So there's a major assumption in checking in on April 1st SWE in a lot of our sort of reservoir rule curves and different things, an assumption that it will always be around. On the right there is now looking at the hydropower facilities and also our population centers. And so we have to convey water to these places, reservoir inflows into the hydropower facilities is really important, but then we also have to convey that water to population centers way far away from those places. And so those are sort of the mean trends over the last few decades. And what this talk is primarily going to be about is about extreme events that really reshape those seasonal, intra-seasonal sort of dynamics of snow. So we're going to talk about sort of two things here. We're going to talk about rain-on-snow events, which are often caused by atmospheric rivers, which I mentioned earlier. And they're associated with about 81 or 82% of all flood damages across the West over the last few decades. And on the lower left there, this is an example of some satellite imagery of an AR making landfall, and the green area is a bunch of rainfall that occurred during that AR event, especially high up in elevation. On the right here, this is sort of newer research than I've been a part of, is this idea of a snow-to heat wave. And what we're finding is that when you identify these events, and I'll get into the conditions that we use to identify those events, you typically double snow melt during these events. And so on the lower right-hand corner here is a NOAA-SIRA satellite animation of the snow-to heat wave event we experienced in March that led to that downward curve on that plot I was showing of Lake Powell plus snowpack. And what you can see is that there's a well-defined ridge or a place where there's no integrated water vapor is what is being shown there, and it diverts that high-pressure system associated with the snow-to heat wave event, diverts what's an atmospheric river there further northward and prevents the building of snow during a time when we still need to build snow before April 1st. So they sort of ablate that snowpack, and we'll get into a little bit more about that in a little bit. Another thing is that in the Hyperfastest project I'm a part of, we've been using these things called storylines, or sometimes they're called object lessons, to sort of contextualize these extreme events. And the idea is to use these extreme events to learn from them and to proactively anticipate and adapt to how they might respond in a future climate, maybe decades from now or a few decades. And so we're going to use two object lessons that could be representative of the next few decades as we continue to warm and snowpack becomes more susceptible to abrupt ablation. So on the left here, this is a diagram from a paper that just got accepted a couple weeks ago on the snow to heat wave work. So please feel free to scan the QR code and you can check out this figure. But we tried to distinguish what a rain on snow event, the causality of it from an atmospheric perspective and from a snow energy mass balance perspective, and fluxes, why the conditions for a rain on snow event are different from a snow to heat wave event. And again, the rain on snow events are primarily liquid precipitation, windy ventilation of warm, moist air over the snowpack that creates a latent insensible heat flux into the snowpack. And rain on snow can both build snow water equivalent and can also decrease it through melt. And there's some nitty-gritty details about the processes at the bottom left there. And then snow to heat wave events are, again, associated with these amplified stationary ridges of high pressure. They're strongly anomalous positive temperatures that persist for multiple days above freezing, both day and night, which is important because it erodes the cold content or the energy needed to overcome to start melting the snowpack. And they're usually associated with warm air advection and subsidence. And so that can lead to that doubling of snowmelt that I mentioned. So we're going to talk about two specific events, though, to contextualize all this. So the 1997 New Year's flood event, which is sort of the design storm for a lot of people in California and the Department of Water Resources. They consider that to be sort of their 200-year event. And then this May 1983 event, which is, I feel like, kind of been forgotten, at least for younger folks like myself. But it was really amazing at what happened during this event, and it really impacted Glen Canyon Dam, impacted Utah, and impacted Colorado. So I'll get into that later in the talk. Okay, so this 97 flood event, I'm just going to give some context on this. So on the left here, this is an animation, just FYI, some eye candy of the simulation that we actually produced to recreate this event. So this is using the U.S. Department of Energy's flagship Earth System model, E3SM, with regionally refined meshes. And what's being shown here is sort of the atmospheric river making landfall and the precipitation associated with that in light yellow to green. And then also we're showing sort of snow-covered area and snow water equivalent and the ablation of that over the sort of the event that was. We tried to recreate the event that was. And what's pretty amazing about this event is it's the most costly flood still to today in California history, about $1.6 billion in damages. At least 0.5 million people were displaced by the flooding, and most of the California counties were declared disaster zones, and there was a lot of agricultural damage and whatnot. And I just want to highlight two images here showing how widespread this flooding was. So in the northern part of the state, in a place called Marysville, Yuba City, the rivers swelled so high that there's some levees here. I don't know if that's easy to see. Unfortunately, the levees held, but it was almost an overtopping event that would have inundated the entire city, or both cities. And all the way down to places like Yosemite, which is further south there. This is an image of me of a sign in Yosemite Valley commemorating this event on January 2nd, 1997 at 11 p.m. That was a high water mark there. It's about 8 feet high of water that inundated the whole area. So about a shack's worth of water inundated that area. So it's pretty spectacular and amazing. So we have multiple studies about this event. So we did sort of like a validation study, dialing in E3SM, and then we did a what if scenario of like, what if this event was recreated in a cooler planet or a warmer planet? So I'm not going to talk a lot about the validation. You kind of have to believe me that we dialed it in and it's doing a decent job. And I'm more focused on the warming level analysis, but I'd be happy to talk about it if you have questions, the validation. Okay, so the reason why we use regionally refined mesh is that we're sort of using an Earth system model like you would a WRF model or a downscale model, right? But you're doing it internally consistently within the same model. And so what's really beneficial is that you're getting the synoptic scale conditions, the atmosphere-ocean teleconnection responses all within that same model. As the storms are then influenced by those synoptic scale conditions or mesoscale, they're coming into this regionally refined mesh patch, and then as you have higher resolution, you can better represent things like topography, land sea gradients, et cetera. So then as those storms start to interact with topography, you get better estimates of the freezing level in the mountains, rain snow partitioning, building of snow, antecedent snowpack, soil moisture levels. And so what I'm showing here is that if you were to run E3SM at 1 degree resolution, which is shown right there on the right, I know it's flickering a lot, that would be sort of what a typical IPCC Earth system model would provide you. And as you can see, the elevations of the Sierra are sort of smoothed into the Rockies. So you're almost making the Sierra a part of the foothills of the Rockies. But as you get to kilometer scale, which we ran the model at around 3 kilometers or so, you start to resolve the Sierra Nevada, its land sea contrast, its valley, its Sierra Nevada in a much more clear way. And so, like I was saying, we're using this tool called BetaCast, and that's what I've been helping Jacob to get spun up on. And he's going to help me work on some flood events, and he's going to work on some he's interested in too in the coming years, kind of like this 97 flood event. And so what we can do is we can recreate this event with 3 different resolutions, so different regionally refined mesh patches at 14 kilometer, 7 kilometer, 3.5 kilometer. So we can identify the necessary and sufficient resolution to represent different flood drivers during that event. We then use the model kind of like a forecasting tool, like a weather model, which is not necessarily designed to do, but you would start it with an initial condition at different lead times, so 4 days out, 3 days out, 2 days out, 1 day out from the actual flood event. So we created 6 forecast lead times with those 3 different resolutions. And then we also played around with warming level. So what if you preconditioned the land surface and the atmosphere at, say, 1 degree of warming, 2 degrees, 3 degrees, or a pre-industrial climate using LENS? The large ensemble here that's produced here at NCAR. And again, these are enabled by sort of this thing called BetaCast, which you can go to Zarzicki and Jablin, or Colin Zarzicki is the lead developer of that. And you can get more information about it there. There's also a GitHub if you're interested. So essentially, this is what the initial conditions would look like. So these are the traces. I wouldn't expect you to read this, but it's just showing that each row is a different forecast lead time. So the top row would be forecast lead time of about 3 days, 4 days out before the flood event really peaked, all the way down to like a couple of days out. And we really wanted to see how that forecast lead time shapes storm total precip, changes in SWE, runoff, et cetera. And then using some other workflows, we were able to track the atmospheric rivers and calculate what's called an AR category scale. These AR category scales are useful in terms of kind of giving water managers an understanding of would this flood or would this AR event produce flooding primarily, or would it be mostly beneficial and replenish reservoirs. So we have a bunch of workflows if you're interested using tempest extremes to calculate all these different things. And I'll show some plots later on with the 97 flood using these techniques. And before I go on to with the warming level analysis, I just wanted to quickly say that in order to recreate pre-industrial conditions, contemporary climates, all the way up to 1.7, 2.5, and 3.5 degrees. So we did essentially 6 different warming levels, including the event that was, which is called the control simulation. These are showing like average temperatures across the globe, and then the deltas on the right there. And those deltas are coming from the CSM lens, extracted at different time periods when you hit about 1K warming, 2K warming, 3K warming, 4K warming, and you're applying that on top of the conditions in Era 5 around the 97 flood event when we start the forecasts. And then we also do a land surface spin up, and you'll see some animations in just a second showing that 5 years prior to the event, we also do an offline land surface model simulation where you're giving it that Era 5 data with those deltas, and then you're spinning up the land surface to sort of build snowpacks or deplete snowpacks in a warmer, cooler world as a result. Okay, so as I was mentioning, we really wanted to assess each flood driver and see how resolution dependent it is, how does forecast lead time change that, and how warming level changes that. So this is showing the control simulation here. This is the 4-day sort of peak portion of the event when the atmospheric river made landfall in the control simulation, so the event that was. So on the left there, this is integrated vapor transport stepping through each day. And you can see the AR event sort of makes landfall right when the actual event happened. So it started really to happen on December 31st and through January 1st. And then on the right there is the AR categories reached during this 97 flood event. And you can see that Category 5 was reached throughout the Bay Area up through Sacramento Valley, where a lot of that flooding I mentioned earlier happened. So this is kind of saying that the integrated vapor transport and the duration of this event is sort of in line with the flood inundation that actually occurred. So it's kind of highlighting that this metric that was developed by Scripps folks might be a nice proxy for flooding during an AR event. So now I've created postage stamps of the same animation and same AR category scale reached across all the different warming levels. The top row would be the event that was, so the 1997 flood event. Now, if you took that event and recreated in a pre-industrial climate, a contemporary climate right around 2019-ish, 1.7 degrees of warming, 2.5, and 3.5. And you can kind of see that from pre-industrial to control, there's not a lot of difference in the area at which high severity air category or category 4 and 5 was reached, meaning that this event was already probably very rare and weakly responding to warming. But as you get down to 1.7, 2.5, and especially 3.5, that area of category 4 and 5, so mostly hazardous or primarily hazardous conditions, starts to expand across more of the northern part of the state especially, but also down into the southern part of the state. Yep.
What atmospheric fields did you perturb in the experiment? Was it just the temperature?
We did, yeah, that's a good question. It's been a little while.
I'm sorry, I asked you the same question yesterday.
Yeah, it was definitely temperature. So BetaCast has a lot of functionality, and you can perturb radiation fields, humidity fields, and temperature. And maybe I would just say, maybe we can talk offline about it so I don't misstate, but it's in the paper, especially in the methods. Yeah. So I can't show you all the different warming levels because it would create too many postage stamps there, but the papers have all of the postage stamps and the different warming levels if you'd like to look at them. But we evaluated each warming level according to different flood driver estimates here. So on the top there is the magnitude of storm total precipitation that occurred during the event in the control simulations to the event that was, and the snowfall partitioning during that event, where it got upwards of 60% snowfall, especially in the High Sierra and the southern parts of the Sierra. And then storm total precipitation was upwards of 600 millimeters over that 3 to 4 day event. And then we're showing deltas at the different warming levels further down. So storm total precipitation, pre-industrial minus control. So you can kind of see that there's a little bit of noise, but generally it's about the same sort of event. Snowfall partitioning was interestingly a little bit lower during this event. In the pre-industrial climate at 1.7, and sorry, these are the 6 ensemble members or forecasts that we did. These would be the ensemble average, so it's not just one member, it would be over multiple members. At 1.7 degrees of warming, you start to see less precipitation actually occurring in the northern part of the state. Less, but more in the southern Sierra Nevada. And then as you get to about 3.5, so the highest warming level we evaluated, you're getting more storm total precipitation across most of the Sierra Nevada, but significantly less snowfall by about 40 to 50% across most of the Sierra, especially in the mid to high elevations. We evaluated something called precipitation efficiency. So it's a metric trying to evaluate how much of the integrated water vapor was actually extracted during the event. So we would take storm total precipitation and divide that by storm total IWV. And so that ratio kind of tells you the percent of IWV that was extracted over those 4 days of the event. And what's interesting is that in a warming world, that precipitation efficiency goes down, meaning over mountains, especially in the High Sierra and Northern Sierra, the mountain becomes less able to extract as much integrated water vapor as the event that was, even though you're getting more storm total precipitation. We also looked at max total precipitation. We outputted fields at about 3 hourly frequency. And interestingly, we also see that you get higher amounts of 3 hourly max precipitation rates throughout the Sierra. And that's important because not only the storm total amount matters, especially for floodplainin, but how the stair step of how you get that storm total accumulation matters too. And so we're seeing that in a warmer world, you might get more of these bursts of rainfall that's happening during the event. And so to really highlight this to you more cleanly, hopefully, we were seeing that on the x-axis here, we're showing violin plots for pre-industrial through 3.5 degrees of warming. We're looking at the windward Sierra Nevada, so that's on the lower left plot there. That's the shapefile that we use to extract precipitation estimates. And we're looking at the percent change in storm total precipitation during that event. And then I calculated using the Clausius-Clapeyron theoretical scaling relationship what you might expect that precipitation scaling to be with warming. And so that's the black dots overlaid on the violin plots. What you're seeing from a storm total perspective is your sub-Clausius-Clapeyron during the event. But if you get to really high resolution, and sorry, I guess we outputted 10-minute precipitation rates, not just 3 hourly. What you're seeing is that you're getting super Clausius-Clapeyron scaling at that 10-minute precip rates, meaning that things are becoming flashier throughout the Sierra, or at least over the lifetime of the event. And that has important implications maybe for local scale flooding and some other things that water managers think about. So we're seeing this difference in precipitation scaling between a storm total perspective and this sort of very high frequency output. So now to focus in on the snow side of the equation and some of the dynamics that happen there, I'm showing animations now of the control simulation on the left, stepping through the entire event every 6 hours. And then and you can kind of see that, there's a larger extent of snow available to melt at the beginning of the forecast, whereas at a 1.7 and a 3.5 degree warming level, we've done that spin up process in the land where it's already experienced that level of warming at 3.5 degrees, 1.7. So there's less snow to ablate. And it's also a little bit more ripened so that when the rain on snow event happens, more of that can melt out, especially in the High Sierra further south. And to show that a little bit more explicitly now, so I'm making these same sort of control simulation plots at the top. This is for the start of the event, so December 31st, the magnitude of snow water equivalent in meters on the top, and then difference plots as we go down for pre-industrial control and, 1.7 and 3.5 degrees of warming. And what we're seeing is that as you get warmer and warmer, more of that snowpack is activated across the Sierra Nevada, and so there's more melt that occurs during the event. On the right here now is looking at storm total runoff, so the 4-day total of runoff everywhere. And what you can kind of see is that in the pre-industrial climate, there's more variability. Maybe you get a little bit more runoff, a little less in different places, and that could have been due to the antecedent condition buildup on that land surface model spin-up process. But as you go to 1.7 and especially 3.5, you see less runoff occurring in the northern Sierra where most of that flood event occurred in sort of Marysville, Yuba City, and it shifts further south into the middle part of the Sierra Nevada and High Sierra, where usually you would build snow and maybe have less ablation occurring. And so that's really important for California because a lot of our infrastructure that's more resilient to the 200-year event or higher is in the northern Sierra, and infrastructure that's been built for less than that is further south. So the shifting of that flood dynamic in a warming world might shift further south in the Sierra as a result. And part of that is, and we get into more process level analysis in both papers, but we looked at cold content, which again is that amount of energy you need to overcome to start to create melt, or any additional energy that you put into the snowpack will lead to melt. And so zero cold content would essentially mean any additional energy would then be sort of put towards melting. And so already during this event in the control simulation, there's a widespread area of zero cold content throughout the Sierra Nevada. And then as you sort of move to higher levels of warming, that cold content is reduced systematically, especially in the mid to high elevations of the southern Sierra. And that's partly why we saw maybe more storm total runoff during the event. The other thing is that there's the vected energy of the storm. So that's the amount of energy that rain droplets and the ventilation over the snowpack would have contributed to the melting of snow. And that's not really encapsulated in the model approach we have, but we did this diagnostic assessment of if this wasn't it, how much more advected energy would you get? And so as you can see in the 1.7 and 3.5 degrees of warming, the blue regions would mean that there was no snow to add advected energy to. And then wherever it's red is where there's additional sort of rain on snow potential if that process was factored into the model. And so it's primarily in that mid to high elevations in the lower Sierra, or sorry, further south portions of the Sierra. So another part of my job is to sort of talk to water managers and try to make sense of the jargony things that we do with models or kind of wonky things. So I try in my talks now to distill what I think are some of the main points of the study and distill it in a way that hopefully is more understandable. So peak rain on snow really hazard potential is accentuated about 1.7 to 2.5 degrees of warming because you can still build near normal snowpacks, but they're more ripened and available to ablate during rain on snow events or other extreme events. And so this has implications, I think, for something that California is really interested in and maybe other parts of the West in this thing called forecast informed reservoir operation and how maybe activated they assume the headwaters might be and how much flood pool level they might need behind the reservoir. Rain on snow events could also include more intense short duration rainfall, so that might have repercussions for local flooding, especially in places that have more impermeable surfaces. Again, precipitation scaling with warming at multi-day versus sub-hourly is different, so maybe that might have a change in how engineers think about IDF curves, which they use for building standards or creating stormwater management or something like that. And then flood hazard seems to shift from the northern Sierra to southern parts of the California, Nevada, with more enhanced lee-side spillover, which I didn't really talk about. So there might need to be more infrastructure investments in monitoring networks in these places because we don't quite have the standards that might be needed to combat a rain on snow event like this. Okay, so we're going to switch gears a little bit now and talk about this other 1983 event that I mentioned. And this is a different driver of snowmelt extremes. So this is an example of a snowed or heat wave. And pretty remarkably, in 1983, in late May and early June, the Great Salt Lake so basically what happened is that there was a healthy snowpack season in 1983, and it built up to pretty high levels. And then during this late May, early June period, it rapidly ablated and came downstream throughout the upper Colorado. And the Great Salt Lake rose by about 4 feet, which is pretty remarkable after this event. And places like Salt Lake City had to create artificial canals in the middle of the city to sort of convey that water out of downtown. And if you go to the archives, which is on that QR code there, you can actually see kayakers like kayaking down the downtown of Salt Lake City. So it was just amazing how much flow was happening during the event. And pretty remarkably too, Glen Canyon Dam, further downstream, was receiving so much inflow rates and at a faster rate than was forecasted that essentially they had to put, and it might be hard to see here, plywood on top of Glen Canyon Dam reinforced with rebar such that the dam wouldn't overtop and create destabilization of that dam. And so, there's some really good documentaries about this event, and it's just pretty remarkable that it could have been a lot worse than it was. So it was kind of a near miss, but also created a lot of impacts. Okay, so to sort of like explore this event and the drivers of this event, we used this data set called the 20th century reanalysis. And this reanalysis is really cool. It provides a reanalysis estimate going back to the 1806 all the way to about 2015, 2016. And what is being shown here is every year is maybe like less than a second. But what it's showing is each dot around the globe is a surface pressure estimation around the globe from either ship logs or stations that then constrain this 20th century reanalysis model to estimate all the different variables you might get from, like, say, an Earth system modeling approach. And places where you see kind of cloudiness or gray would be places where there's no information being assimilated. And so they create an 80-member ensemble of this 1806 to 2015 period to kind of assess variability in estimates based on when you're constraining the estimates based on these observations and where they're available in space and time. So we had an idea to take this data set to assess sort of snowed or heat wave events But before we could do that, we needed to sort of identify the conditions that we think would be necessary and sufficient to start to resolve or isolate these events from these atmospheric fields provided by 20th century. So all we're using for this, we tried to make it as simple as possible, is using 2-meter air temperature. On the left there would be for the 1983 event, stepping from May 27th through the 31st, which was the peak portion of the Snowder heatwave event. On the left there would be the anomaly from a background climatology of the temperature anomalies during that event. And then on the right, we're using tempest extremes to extract, using the conditions on the right here that are listed, the conditions that would lead to what we deem to be a Snowder heatwave event. So we deemed that these events should be an event that occurs between March 19th and in July 1st, so sort of in the spring season when you might have the most amount of snow to ablate. Temperature must be above freezing, again, to start to activate that snowpack. It should be very anomalous for that time of year relative to, and we use 3-hourly data to assess that T2M anomaly. And then that T2M anomaly must be sustained above freezing both in the day and the night to erode cold content and lead to sort of the ablation of the event. And then those criteria should be sustained for at least 3 days. Some of these choices, we wish we had sort of cold content measurements to dial that in a little bit more of like maybe we don't actually need 3 days, maybe it's snow responds a little bit quickly, like 1 day, 2 day. So that's sort of next step things, or if anyone else has brilliant ideas on how to refine this methodology. But we thought 3 days is sort of used in the heat wave sort of metric world. And also after 3 days, you would expect maybe the snowpack to, ripen and then be susceptible to melt. So 20th century provides snow order equivalent, but it wasn't very skillful for what we were trying to look at. So instead, we swap in the temperature index model called Snow 17, which is still actively used by the National Weather Service to do forecasting. And so you can go to their GitHub and read a little bit more about the model, but it really only needs temperature and technically precipitation. But we don't use all portions of the model. So this is a flow diagram of the Snow 17 model. So it takes in precip and air temperature and does all these different submodules and whatnot. But we just take the surface melt estimator of that model. And in that model, the surface melt model, what's shown on the left there are parameters, which I'll get into in just a second, that you dial in at a SNOTEL site where you might be using the model or over a larger area. And then it'll give you an estimate of how much melt might have occurred if snow is there. So it's kind of a high-end estimate of melt. It doesn't necessarily account for snow that's on the ground. It would just tell you if snow is on the ground, what's the maximum amount that would melt. And so this is the equation for that snow melt potential. It has that temperature index side of the equation on the left there, and on the right, they actually add a light rain on snow factor. For our work, we just actually ignored the light rain on snow. We made the assumption that during Snowder heatwave events, you wouldn't have co-occurring rain on snow events. And that's something we actually had to investigate thanks to a helpful comment by the reviewer that's now in the supplement about how often do the rain on snow and Snowder heatwave events co-occur. And they actually sometimes co-occur, but not significantly. And so I would just point you to the paper and that for that. But we just assumed that light rain on snow will not influence our results. So the TA is where temperatures from 20th century is coming in, and then use this thing called M-base, which is the assumption of when you might start getting melt potential starting to occur. So we used just freezing for that. So it would read in every 3 hours the 20th century reanalysis, and anytime you're below freezing, it would start to calculate melt potential. In the melt factor portion of the equation here, it has these sort of parameters I was mentioning, MF max, MF min, and some of these other parameters here. And I'll just explain what these are trying to accomplish. So on the left-hand side there, those parameters are trying to assume things about length of day, latitudinal dependence of melt based on sort of solar radiation and length of day and things like that. On the right-hand side, like MF max and MF min, those become more or less important throughout the season. So MF min is more important during snow melt in the midwinter. MF max is more important during the spring season. So we really focus in on just that parameter to dial that in. And these MF max, MF min parameters are supposed to, in a physicsy way, quote unquote, do land surface feedbacks like aspect and tree cover. And if you go to NOAA technical guidance documents, they'll tell you what the range of MF max and MF min should be for coniferous forests, mixed forests, things like that. So one really cool thing is at Berkeley Lab, I get to work with statisticians, and they really make my work way better than I could ever do on my own. And so they employed Josh North and Mark Risser helped to develop a model, a statistical model, that will estimate these MF max parameters, plausible ones. When you give it SNOTEL information, and you estimate snowmelt potential, and then you optimize that MF max parameter. So we essentially created a 50-member ensemble. We created more of a large ensemble, but then we used 50 estimates from that to then create a parameter ensemble. And what I'm showing here is just of those 50 parameter estimates, what the MF max value would be across the West. And then I'm just outlining places where there are mountains, because the snowmelt potential will be estimated outside of mountains and places where you might not get snow. So we just tried to mask regions where there's likely just to be snow, which is in mountains, right? So, or at least in the West. So we then mask out estimates of melt potential in just those regions. Okay, so you might be asking now, that was a long explanation of the model, how good does it do? And so what's shown here is that with this 50-member ensemble optimized using this Bayesian approach, the blue line, or the trace of it, is being shown from 1983, March 20th through June or late June or July or start of July. And so the light blue trace would be the Snow 17 estimates. SNOTEL would be in black, and that would be averaged on each day across all of these dots on the right-hand side of the plot here of all those SNOTEL sites, and then we're comparing the nearest grid cell that we're producing snowmelt potential from Snow 17 in that blue line. And what you can see is that we also identified the snow eater heat wave event, and it occurred sort of at the peak of the negative D SWE during the event. 10 minutes, okay. And so what's shown here is that the Snow 17 model can kind of get the mean melt correct, but it's kind of weakly getting the 90th and 10th percentile, so the more extreme melt correct. And that's those thinner lines that are shown surrounding the mean melt. And so SNOTEL is saying that you should get upwards of 70, 80 millimeters on average across sites during this snow heat wave event in 1983, whereas Snow 17, out of the box at least, is giving you a much more constrained answer. So in our paper, and I don't have time to go over this, we actually added a new additive term to Snow 17 because we didn't want to, we wanted to try to keep the model as is and see if we could add a cheap computational way of enhancing melt on snow heat wave events. So we have this additive term. I'm not going to go over it in this talk, but in the paper, there's a few different additive terms that we tried out to see if we can get better extreme melt potential from Snow 17. Okay, so that's for the 1983 event, sort of as a storyline or a case study. This is now looking at the climatology over the SNOTEL records, so from 1980 to 2015. Similarly, unfortunately, the x-axis is cut off here, but it's again ranging from March 19th through July 1st. And so this would be the average climatological melt potential or negative D SWE from SNOTEL on each day. So on the left, these would be all days, so including snow heat wave days and non-snow heat wave days. On the right would be on snow heat wave only days. And what you can see is that Snow 17 does estimate sort of the mean potential correctly, but it seems to underrepresent, especially on the snow eater heat wave days, less or more constrained sort of estimates of what actually happened. But on snow eater heat wave days, whether it be SNOTEL derived or the model, we saw a doubling of TICPL's Western US snowmelt rate. And I alluded to this earlier in that summary diagram, but we looked across all of the events from 1980 to 2015 and made composites of the geopotential height anomalies. What we're seeing is that generally these snow heat wave events are associated with ridging events, high pressure ridges that lead to this sort of ability for the snow to ablate and rapidly melt and double the snowmelt rate. So another way to look at this is we also went back to, because we used the 20th century reanalysis, you can go all the way back to the 1850s, or in this case, 1950s. And each year is represented as a row in this plot. And each day from March 19th through July 1st is shown on the x-axis. And what this is showing is days when a snow heat wave event was identified, and the more red the event, the more strong that snowmelt potential was that we estimated. But we generally found that we get about 3 to 5 events per year that last about 3 to 5 days per event. And what's overlaid here are these superflood events identified by Trulli et al. In this really nice 2021 paper, and that's why we went back to 1950 to 2010, is that they identified superfloods over that same time frame. And overlaid there are and sort of bold dots would be events, superflood events that coincide within a day or a couple of days of when we identified a snowed or heat wave event. And open circles would be where they were spring snowmelt dominated events, but not associated with a snowed or heat wave event. And what was kind of a proof of concept, or see if we're a sanity check, is that 7 of the 11 spring season snowmelt dominated superfloods, like the 1983, were identified in close proximity to these superflood events. So now going back to the 1850s, this is now showing trends in the characteristics of these snowed or heat wave events. And so what we found is that since the 1850s, on the left here, that's showing heat wave, snowed or heat wave average area, massed again over the mountainous regions and whatnot. So these snowed or heat wave events have increased in area by about 102,000 kilometers squared per century. So there's a statistically significant increase since the 1850s in their area. So, their durations, interestingly, are shortening by about a quarter of a day per century. So you're getting larger sort of areas, but shorter durations. And more of these events are starting to happen sort of more per seasons, between March 19th and July 1st. And their seasonality of when they can first occur is shifting earlier and earlier. So back in the 1850s, it might have been very rare to get a snowed or heat wave event even in April or May, and now at present day, it's getting more likely that you can get them in March, like we just experienced. And so this is sort of unfortunate news for water managers, because this is yet another maybe snowmelt extreme driver that they might need to think about. So again, I'm just summarizing here. I know I'm maybe running out of time, but the snowed or heat wave events were associated with, again, 7/11 spring snowmelt dominated Western U.S. superfloods since 1950. So this probably has implications for snowmelt forecasting, especially in the spring season when there's a lot of assumptions being made on how much water might come into reservoirs, how much might be available to allocate to agricultural users or urban users. Melt season snowed or heat waves typically double snowpack loss, and we saw this not only in just model results, but at snowtel sites as well. And so a next step question, because the model we used is a simple temperature index model, we can't get it like, where does the snow go? Does it always come out as abrupt melt, or is there also sublimation that's occurring? So we would like to explore this, and I'll show you some preliminary results using E3SM to explore this. But that's sort of a question too, is like, where does the snow go during these events, and how is that shifting in a warming world? Extreme melt rates are underrepresented by operational melt models like Snow 17. So this is really important for reservoir inflow forecasts, kind of like what happened at Glen Canyon Dam. They were saying that the inflows were estimated at much lower amounts than was actually happening. So we tried to provide a path forward for that. I don't think we used the best approach, and there's a lot to be desired still. So I still think that's something that needs to be developed in Snow 17 and other operational melt models, is how to account for these nonlinear changes in snow melt during these extreme snow melt drivers. And so since the 1850s, Western U.S. snowed or heat waves have increased in area and frequency, decreased in duration, and shifted earlier in the melt season. So this has important implications for headwater management and assumptions about that. Okay, so I'm going to show you some very preliminary work, but again, we're just showing regionally fine mesh grid that we've developed over across the Western U.S. up through Canada at about 3.5 kilometer resolution, and we're trying to get all of the West resolved at 3.5 kilometers so that we can look at these large-scale snowed or heat wave events like in 1983 and other events. And so again, we're using that regionally fine mesh because we want to resolve topography much better than what you can get from a typical Earth system model. And these are very preliminary, but this is again showing sort of snowpack at the start of the forecast that we're doing for the 1983 event. And it's showing that, you know, snow water equivalent across the West on the left at the start of the event, sort of the density of that snow. So it's already sort of really wet and susceptible to melt. And the cold content is shown there. So again, a 0 cold content means that with any additional energy, that snow is really ready to melt. And then on the right here, I just wanted to highlight that, you know, folks are always wondering if these events co-occur with rain on snow events. And what we're showing for at least this event is during our forecast, there's very little advected energy, which is a proxy for that rain on snow event throughout the West, meaning that this is primarily driven by that ridging and this snowed or heat wave event. And so this is sort of a preliminary estimate of, again, showing a time series of the 14-day forecast during the event. On the left there would be the area at which you experienced at least 10 millimeters to 100 millimeters of DSWE on the left, simulated by regionally fine mesh E3SM. And then those dots there are the snowtel sites, and we're comparing our estimates of negative DSWE, which is in blue there on the trace on the right, over the 14-day forecast relative to SNOTEL. So we're kind of getting at the negative DSWE response that was experienced during that event. And then we're comparing it also to Era 5 land. So we're showing enhanced melt even relative to Era 5 land. And so we're still working on dialing in this experiment to sort of optimize it and get it better. The idea is to then use this experiment to understand where does the snow go, some of the nitty-gritty processes that happen in the headwaters, and maybe how different the Rockies respond relative to Sierra or Cascades. So be happy to take any feedback if you have any bright ideas to use this experiment. And so I just wanted to highlight, because I think it would be a little bit weird for me to not talk about the March 2026 event, because history doesn't necessarily repeat itself, but it often rhymes, as Mark Twain once said. And so the 1983 event versus the 2026 event, we didn't have widespread flooding necessarily, so maybe more of that event resulted in sublimation or something like that. So it'd be really neat to sort of use these approaches that I just mentioned with E3SM to maybe recreate this event as well, understand that. But again, we didn't do that. But I just wanted to highlight that these are satellite images of before and after February through March of this event. This year Nevada still had sort of a poor snow season, even though it was near normal precipitation. And so we were about 67% of normal snowpack levels on the left there on February 27th. After the snow or heat wave event happened that I just showed in the animation in the previous slide, we went to about 18% of normal right before April 1st. So a lot of decision makers in California were really worried about that. And then because these events are so widespread, due likely to the ridging and whatnot, the Colorado Rockies also went from sort of, it got down to about 24% of average after this event. And so that also has implications for the ongoing issues with the Colorado River and overallocation and whatnot, in that, So again, water year 2026, kind of like I was saying for water year, or the storylines of 1983 and 1997, could be an object lesson for the next few decades, where these are showing plots of California temperature, where we're receiving near normal precipitation, but highly anomalously warm temperatures, especially throughout the Sierra Nevada and mountainous portions where we build snowpack. So we had low to no snow as a result. And then these extreme events that played out, maybe in different sequence than happened previously in, say, 1983 or 1997, you had this sort of warm spell event. So on the right here, we're showing average snow is the sort of light blue region, and then the current year is the trace there. And what happened in this year is that we were sort of building snow near average. Then all of a sudden we had a warm spell that happened. And then we built snow again through an atmospheric river. But one of the atmospheric rivers that happened created a rain on snow event that ripened the snowpack, lowered the cold, or upped the cold content closer to zero. And then we had this snow or heat wave event that rapidly bladed the snow. And then around April 1st, where we check in on our water content, we're about 18% of normal at that point. And then we had a flurry of storms, which is kind of weird. And it just kind of rock skipped the water year in terms of snow, rock skipped, and didn't really help a lot, but at least it helped a little. And so that's where we're kind of currently at now. We're really below normal for this time of year. And so I think hopefully you got from this talk that we really need to start thinking about the 21st century and revisiting a lot of assumptions we make with the 20th century mindset. And I think this quote from a paper I was a co-author on with Sasha Gershinoff and others really succinctly says it, where California at least must learn to derive more of its future water resources from less reliable snowmelt, fewer storms, and more punctuated floodwater, and sort of to be more proactive rather than reactive to these things. I think these 5 bullet points are really nice science forward strategies to start to be more resilient and proactive to these snowmelt extremes. So maintaining our current SNOTEL network and other monitoring networks is really important, and expanding the monitoring networks to sample things like cold content measurements I think could be really useful across the West, so that way we know how close to melting our snowpacks are, and using more remote sensing strategies like the airborne LiDAR, ASO campaigns, et cetera, and satellite-derived estimates to understand and constrain how much uncertainty there might be in the water amounts in our snowpacks and how much we might expect as reservoir inflow. Maybe maintaining and more nimbly managing our water infrastructure is important too. So using things like forecast-informed reservoir operation, where we have different spillway heights and we can manage our reservoirs at a more week-to-week basis rather than month-to-month or season-to-season. That might be really important. And the idea maybe would be to convey that water once you release it to agricultural land or a floodplain, and bank that water more regularly in the ground through things like managed aquifer recharge or floodplain management, so that you can then extract that water at a later time in the year when you need it. And then, of course, more efficiently utilize our current water and generate new water, quote unquote. So things like direct potable reuse. There's a project at Berkeley Lab called NAWI trying to investigate new technologies such as direct potable reuse, how scalable that might be, creating these sort of trailers that you can move around for rural communities where you can take wastewater, sort of clean it up, and then use it again a second time or third time. And then I think I'm a little bit biased in this, but the Hyperfastest project I'm a part of in DOE sort of promotes engagement by scientists and myself to talk about what's keeping them up at night, what are they facing as water managers, and how we can make our sort of virtual laboratories or system modeling approaches more useful to them so they can proactively plan for these future snowmelt extremes. And I think we need more of those partnerships between academia and management, and it's not invested enough, in my opinion, at least in DOE circles. And so with that, probably, oh no, actually I got a couple minutes, yeah. So I would be happy to take any questions. Sorry, I didn't answer your question earlier. We could talk offline. Feel free to email me. I also have a webpage if you wanted to sort of monitor other things I've been up to. I have a social media account. I'm not very active on it. I don't know if that's cool anymore. And at the very least, enjoy this photo of Luna enjoying some infrastructure just upstream of me during a spring snowmelt season last year. And she was very happy about it. So I hope you are too. Thanks.
Great, yeah, questions in the room, and we can take some on Slido as well. Seth.
With the different lead times,
Yeah.
when you're doing betacast, is that what effect does that have? Does that give you divergence because of chaos theory, or?
Yeah, it's sort of like how the storm tracks might play out differently from initial condition. And what we found actually in that first paper that I didn't talk a lot about, we actually created violin plots of like storm duration change in SWE, storm total precip. And what we found is like 4 days out, the AR event was fairly predictable, and they basically overlapped at 12-hour increments. So like the AR event was less responsive to initial condition, but it was, and also like SWE, I think, as well. But if you were to go like 7 days out, 14 days out, we'd probably have even more spread, but we didn't go that far back. Did I answer your question? Yeah.
Do you see this information being used by water managers and infrastructure planners for, like, I don't know, what they intend to do for the coming decades for water resource management?
I hope so. Otherwise, I feel not.
No, I mean, like, have you personally seen it being integrated into their work?
Yeah, so in the Hyperfastest project I keep mentioning, we talk explicitly with people at California Department of Water Resources. We talk with Sonoma County right now, Sonoma Water. We talk with Denver Water. There's all sorts of agencies around the continental U.S. we talk to. And I think it informs them. I don't know if they're directly going to use our exact results because they want to see this result emulated across a lot of methodologies to build confidence. But at least through just discussing it with them, airing the dirty laundry, not just the good results. There was also bad results, right, that we highlighted with reservoir inflows, for example, is not well represented in our model. I think that builds trust and camaraderie and like a realness. And so we're just doing that over time with them. And so it might inform and like flag things in their head when they work with consultants who might go that extra mile of making it completely useful to them. But at least gives them a litmus test of maybe what to think about, what is the physics of what's going on, how things might respond to warming. So I hope I answered your question, yeah.
Were these projects developed in collaboration with those sorts of water managers?
Yeah. And sometimes in certain papers we've offered co-authorship. And depending on how sensitive the subject is, sometimes they don't want to be co-authors, but they'll provide feedback because of the legalese of what might be going on. But we definitely really value their feedback because some of the analyses I did, right? Actually choosing rain on snow event, they actually wanted us to do more rain on snow because that was top of mind for water managers in California especially. And then we iterated on the 97 flood event as the design storm rather than say the ARC storm or some other like 2017 event. It was also a flood event. So yeah, that was an event that was important to them. So
cool.
Yeah. Thanks for the questions.
We have a Slido. Jared Lee says, great talk. Do you have any ideas or insights into why flow over high terrain during ARs is less efficient at generating precipitation as warming increases in your E3SM simulations? I know you can read, so. Yeah, that's a great question. So I have been fortunate to start talking more and more with Nick Seiler, so I'll just give him a shout out. He's been working on precipitation efficiency and how lee-side precipitation especially will respond in a warming world. So I point to his studies, but I think talking with him, he was saying that in a warming world, there might be tropospheric expansion and the storm tracks might
shift a little bit further in altitude, and as they're interacting with orography, there's less of that bump occurring or orographic uplift, and so they kind of cruise over the mountains a little bit more, and they don't hit lifting condensation level and things like that. So it becomes harder for them to extract the moisture as a result. So I think that's part of the question, but it could also be model sensitivities in microphysics. It could be all sorts of things. So I think that's an area of interest that I still have of thinking about precipitation efficiency in a warming world, and especially at different time scales, like storm total versus 10-minute or higher frequency. Hope I answered your question, Jared.
Yeah, I have one as well. I think for the 2026 snow year heat wave, it seems like there's a lot of possibility for compound extremes as well. Like that's a pretty strong AR to be hitting the Pacific Northwest. So have you looked at that association at all to see what other impacts might be happening more broadly?
Yeah, so like I was saying in our paper, we assumed that snow or heat wave events might not co-occur with a rain on snow event. But as I showed with 2026, there was a rain on snow event just before that conditioned the snow or heat wave event to maybe have more of an impact. And I think that could be an area of study of the sequencing of those events. And I still think the co-occurrence, there were some years where you did have co-occurrence, and I would love to know why. Is it like deep convective storms in certain places that happen? It's probably rarely going to be an atmospheric river that comes in because it's such a high pressure ridge area during snow or heat waves. But maybe in the peripheries of it, as you were saying, it got an AR got diverted to Canada. So maybe at the peripheries of the snow or heat wave event, there might be the interaction. So yeah, I think that would be a great area of study.
Well, I think we're at time, but that was an amazing talk, Alan. Thank you. If we could thank him one more time.